Dear friends, after a short break, we are back to our small YouTube channel, AMP Power System Workshop. In this channel, we have already 54 videos which are pertaining to this electrical protection system and sizing of various electrical equipments and its various properties. Now, all these videos I have seen, I have several viewers and subscribers who are our best friends, and based on their various proposal and suggestion provided on these videos, I have planned to address their views as well as their suggestion, and to keep those things in mind, I have now planned to come back to this channel to honor or to address their observations or comments. To honor those observation comments, it is essentially required to create another few videos which can fully cover their requirements. Based on that, I have planned to start to produce the new videos which will be addressing those comments or suggestions or proposals. So if we summarize all the comments and proposals, we can see that most of the viewers and my friends, they have requested to address the short circuit current calculations for the AC networks, as well as some of our friends has proposed to highlights or provide some guidelines about the protection setting for the various protection functions which has been designated to particular equipments. Like a transformer, it has a various functions, protection functions, to address those functions and their settings. So they have requested for. So I have planned to address all those points. So today's session, it will be pertaining to this short circuit calculation. We might be preparing couple of sessions. One session for the short circuit calculation, which will be consisting of couple of videos, and then another sessions will be providing the setting guideline of the various protection functions of electrical equipments. So today's session will be the session which will be consisting only part of this short circuit calculations. Now it might be 3-4 videos. Today's videos will be giving the guideline or the basic parameters which are required to be considered to calculate the short circuit current of an AC circuit. Now this short circuit can be two part. It could be on three-phase short circuits. Another is a which is called symmetrical short circuit or symmetrical fault current. Another will be single line to ground fault or double line to ground fault or three-phase to ground fault. That is an unsymmetrical fault. So what about whether we are going to discuss about the symmetrical faults or unsymmetrical faults? In all cases, we need to consider few parameters which are the basic parameters for to calculate the short circuit currents. So this the basic fundamental parameters, electrical parameters which are required to tabulate or calculate for any electrical fault calculation is the impedance. Now we will discuss today's session about this impedance and how it is to be presented and what is their characteristics. All these things we will discuss today's video. Now this impedance, how the impedance is coming to picture, if we write down the basic electrical equation for the current, voltage and impedance, we know the current in any AC circuit I, that is given equals to voltage by impedance or resistance. In the DC circuit it is called resistance. In the AC circuit we call it Z is a impedance. So what is this impedance actually? This impedance is a special electrical parameter which decide how much current will flow through the circuit. It is actually a opposing force, or it due to these specific properties of any electrical circuit. When a particular voltage or a specific voltage applied to electrical circuit, due to these properties, current flowing through the circuit is getting obstructed. So we can say another way, impedance is a parameter or is a properties of any electrical circuit which oppose to flow current in the circuit when a specific or a specified voltage applied to this circuit. That circuit could be AC circuit or it could be DC circuit. In the case of DC circuit, we said this impedance called resistance. In case of AC circuit, this the parameter is called impedance. We will be coming more detail about this. So in a brief, impedance is a properties of any AC circuit which oppose to flow current in that AC circuit when a specified voltage is applied. So it is some sort of negative properties or negative character. So if the impedance is high, what does it mean? When a specific voltage applied, current in the circuit will be less. Similarly, when the impedance is low, current in the circuit will be high. So impedance is actually current in the circuit is decided by the impedance in the reverse order, or it is a reciprocal. It is not proportional. Inversely proportional. You can say current is inversely proportional to impedance of the circuit. Now this impedance for the DC circuit, we have already said it is only the resistance, but in the AC circuit this impedance has a two parameter. One parameter, this Z, consisting of two parameter. One parameter we call is resistance and other parameter we call is resistance, and second parameter we call is reactance. This is called reactance, we represented by X. Now resistance, we have learned the resistance very well from very school level. Now the reactance also we have studied. The reactance, it will be two type of reactance. One could be inductive reactance, another could be capacitive reactance. Now this, in the case of most of the electrical circuit, it has a resistance as well as inductive reactance. Now this reactance X, what is this? This reactance, how it is created? The reactance is actually, it is applicable only for the AC circuit. Why? This reactance is coming from the inductor. When inductor carrying a current, or whether it is AC or DC, there is a flux links with the inductor. Now, if this flux change getting changed with the time, if the flux is F, if there is a dF dt, that is change of flux with the time, then there will be induced EMF. In the case of DC circuit, except switching on and switching off, DC circuit, there is no change of current in the circuit because this is a constant value of resistance. But in the case of AC circuit, what is happening? The current is not constant. It is a AC, if it is sinusoidal wave like this, suppose it is a 50 Hz, that means in every 1 second, this is a 50 cycle is completing, and every time when it is increasing, flux is increasing. When it is decreasing, flux is decreasing. So due to this change of flux with the time, there is a induced EMF in the inductor coil, which will try to oppose the flowing of current. With that, induced EMF will be acting against the injected EMF. That means that will oppose to flow the current. That's why this reactance is also acting as a resistance. We have like a resistance, means when there is an inductor and there is AC supply applied, then immediately due to the change of flux with the time, there is a reverse force is working to flow the current. So it is opposing that flowing the current. So that part we call is reactance. This reactance, if there is an inductor L, then the reactance we can say this reactance is it is a omega L. Omega means is a 2 pi into frequency. N is the frequency into L. L is the inductor in Henry. This is the way we calculate the X from the inductor. So that in case of capacitor, it will be reverse formula. So inductor, that means when there is a inductor, means there is a inductive reactance. When there is a capacitor, there is a capacitance reactance. That means when we go for the impedance in the AC circuit, we can simply write down impedance Z, that has a two part. One part is a resistance, another part is reactance. Now how these two are related? Now we can, this is the two components. Now how we combine these two components? This component is there is a direction. If I impedance Z is a vector form, then a Z vector that equal to sum of R vector plus X vector. But this X vector, it is actually perpendicular to the R vector. Resistance vector, if we put resistance as a vector, if we consider the direction resistance is working, inductance is working perpendicular to that. That means a resistive current. In another way, when a AC current flowing in the circuit, the current through the resistance and the current through the reactor, we can divide into two different parts. If this current is flowing along the x-axis, reactive current will be flowing perpendicular to this. Due to the change of the direction of these two current, the overall current in the circuit is not in line with the voltage. That means current in the circuit and the voltage in the circuit, there is a phase difference due to this reactance of the circuit. So reactance of the circuit, one property is it is try to oppose the flowing of the current. That is one part. Second part, this due to the reactance of the circuit, the current cannot flow in phase with the voltage. What does it mean? Suppose this is a voltage of the circuit. This is the voltage of the circuit. Now, if the reactance is not there, the current in the circuit will be the same pattern. Same pattern. The way the voltage is flowing, current will be following the same pattern. When voltage is maximum, current is maximum. When voltage is minimum, current is minimum. If there is no reactance in the circuit, so there is no phase difference. But when this circuit has a reactance, then the current will not flow in the same way as that of the voltage. Then immediately current will be out of phase. Then the current may be like this. This, you see there, when it is a peak, it is peak after some time. So there is a time difference. So this phase difference or lagging, this is we call this in the case of inductive current, this is lagging. The lagging is introduced due to the reactance of the circuit. That means indirectly we can say reactance of a circuit has a two properties. One property is to reduce the oppose the flowing of the current. Second property is this reactance cause the current flowing in the circuit out of phase of the voltage. So this is the reactance. Now these two reactance, as this reactance already said, it is not working in line with this current. This resistance, the current which is flowing through the resistance, we call it a heating current. It is produce I square R loss. And the reactance current which does not produce an I square loss, but it produces another type of loss, we call it a hysteresis loss. That is, we are not going to that part. So this resistance and reactance Z, now Z, as it is a different direction of R and X, we cannot simply sum. We cannot simply sum R plus X like this way because it is not the same direction. So to produce this thing, it has a two way we can produce the Z when we are calculating the short circuit current. One way is producing, we call it a polar form, that we write down Z with of angle theta. This is the way on, it is called polar presentation. That means Z has a two component. That component has a, there is a resultant Z has a angle with a theta with one of the direction. Or another way we can produce this when we put in the radial form. This is the polar form presentation. When you go to the produce in the radial form, then how we produce it? We produce by a vector diagram. If we produce the resistance R in this way and the reactance part this way perpendicular, so this is the R and this is X. So if this is the Z, suppose this is the Z and we just make an angle theta. This is the polar presentation. So when we are putting the Z in this polar presentation, this is a Z. Okay, this is a Z vector with an angle of theta. Then Z has a two component. We can make rectangular resolution, we know. This is theta. If this is the R, this component if we say R, then Z equal to Z cos theta. And this will be Z, this equal to Z sin theta, right? So if we produce Z in the form of the polar presentation, then Z equal to how much it will be? This will be Z cos theta plus, at a perpendicular direction means we know, we put by imaginary component root of -1 that equal to I or J. So if we, because in perpendicular direction we represent by -1, then this will be J Z sin theta. This Z cos theta we call the resistance component. So this is equal to R, this is equal to R and this is equal to plus J. Z sin theta means X component Jx. This is the presentation of the impedance. So when we want to produce an impedance in the circuit, we write down Z equal to R plus Jx, where R is the resistance and X is the reactance. Now Z has a unit, we call it ohm. We know that resistance. Similarly, resistance has the same unit, ohm, and X is the reactance, that is also unit is the ohm. This is the resistance, reactance and the impedance relation in this imaginary form, and it is in the polar form, now a radial form. Now from this is the case when we applied Z, we directly apply when we use a series circuit. But when you go to the parallel circuit, then how do we calculate? Suppose there is a, in case of series and parallel circuit, if we look into how we calculate the series parallel combination, suppose there is a one resistance. Suppose, and secondly, this resistance component we know we represent like this, but the reactance component we represent like a coil. Okay, so this is a R and this is a X. Now this resistance and reactance, if we represent, suppose this is one Z, suppose this is R1, this is X1, this is a Z1. Similarly, if I go Z2, there will be another resistance and then there will be another reactance. Now if we go for series combination, then what will happen? Z1 plus Z2, that equals to how much? That equals to resistance component will be summing together, that is R1 plus R2, okay, plus J into this imaginary part will be, reactance part will be summing together like this. So if we have a n component like Zn, then it will be also plus Zn, Rn plus equal J into, here also the same thing, X1 plus dot 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 Xn. This will be the summation of addition in case of series circuit, when all this, suppose this is one unit, this is another unit, all are connected in series. In that case we can get the equivalent like this. Now in case of impedance connected in parallel, then that will be different. We know in case of impedance connected in parallel, the equivalent impedance 1 by Z, that equal to how much? 1 by Z1 plus 1 by Z2, yeah, plus dot 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 like this 1 by Zn. Now in the case of parallel circuit, this will be the equivalent impedance. So in the parallel circuit, to calculate in the parallel circuit 1 by Z, this terminology we define as a different way. We call this is a admittance. This is called 1 by Z, that we call admittance, admittance, okay. This is called admittance. Now this admittance also it has a two part. If we make it as equivalent, so this equivalent will be G plus JB. We call like this, okay, this admittance part. Now, so admittance equal to Y. So if we said admittance equal to Y, I mean if we want to represent the parallel circuit similar to series circuit, then that 1 by Z, reciprocal of Z, we call is admittance. That admittance is equal to G plus JB. G is called conductance, G is called conductance, and B is called susceptance. Susceptance, okay, and Y is called admittance. So in similar way representation in parallel circuit, we use admittance is equal to conductance plus J into susceptance. Here also we can calculate in the same way. Y equal to, this is Y equal to G plus GB. Now Y means 1 by Z, right? 1 by Z if we write down, or this equal to Y 1 by, this is Y equal to Y, that equal to G plus JB. Okay, that is equal to key 1 by Z. Now 1 by Z means key 1 by Z means 1 by R plus JX. Now if I want to correlate the conductance and the resistance and reactance and susceptance with the resistance and reactance, then we have to use this way. We can correlate this X, G is related to R and X, B is related to R and X. Similarly, R is related to G and B, X and X is also related to G, and we can find out the relation. How we can relate? This is equal to, how we can write, if we multiply both by R minus JX, then down will be R square minus J square into X square. Now we know J equal to root of minus 1, J equal to root of minus 1, so J square is minus 1, so this is equal to J R minus JX by R square. This is equal to minus 1, so minus is equal to plus X square. If we equate this to equation, this is equal to G plus JB. If we relate this to, then what will be? This is the real part. So G equals to conductance is equal to resistance divided by what is the divide? R square plus X square, right? And this minus X, this is from here, minus X equal to this part, minus plus JB equal to minus this, that means J cancel, B equals to, or minus B equal to, we can say X by R square plus X square. This is the relation between G and B with R and X. Similarly, If we go the reverse relation, it will be similarly, reverse relation will be like this. If we go resistance equal to how much? This equal to G by G square plus B square. And if I go X, that equal to minus B by G square plus B square. This is the relation amongst this. So whether we represent in series circuit, we represent this impedance in terms of resistance and reactance. In case of parallel circuit, we represent the resistance and reactance in terms of conductance and susceptance. But this conductance, you know, here the conductance is a reverse relation. Conductance is a reverse property. Reverse property means, and resistance or admittance, you can say admittance is the reverse property. Admittance means what we understand in the impedance. Impedance is try to oppose the current. But admittance means, as it is reciprocal of impedance, means it is try to favor it is try to flow the current, means it will favoring the current. That means if the admittance is low, that means current will be less. But if the admittance is very high, in the circuit current will be very high. So admittance actually means, physical meaning of a circuit of admittance means admittance is a property of a circuit which favor to flow the current in the circuit. Now this admittance also has a unit. There is a impedance, resistance, reactance has a ohm is the unit. The admittance, it has a unit. That unit has been given to keep in remember the name of the great electrical engineer or innovator, or you can say who is the industrialist. That is a Ernest Werner Siemens, by whose name the previous company Siemens company is existing. Industrial is a conglomerated, one big conglomerated in the world. The Siemens, which is a all type of electrical instrument engineering equipment they have. But this Ernest Werner Siemens, he was the original innovator of this company. He was basically German electrical engineer, but he became an industrialist, and he formulated this company. He established this company. This company is worldwide renowned, and he was actually famous for this, mainly for the electric tram, electric locomotive, then your trolley cars. All these things is innovation. From that, this company Siemens made, and to keep his name in mind, the admittance, which we said Y equal to 1 by Z, that unit has been given the name of Siemens. That is the new SI unit. But in the old time, this admittance, we used the name Mo. Mo is, it is just reverse of ohm. But in the SI unit, it has nomenclated as a Siemens. So this is the impedance. Now we know the impedance, either you put the impedance or admittance. If you put impedance, you will be putting in ohmic value. If you go for admittance, you will be putting in Mo value or Siemens value. Now this, when you go for the short circuit calculation, the problem of short circuit calculation, the circuit which we will be going to calculate the short circuit, it is not in the one voltage. In the AC circuit, where we calculate the short circuit, any industrial plant, there is a multiple voltage. Suppose I am drawing on a specific or on a general one industrial plant. Suppose there is a generator of 3.3 kV. Okay, suppose there are two generators 3.3 kV, which is connected to a switch gear of 3.3 kV. From there we have a transformer. Suppose it is a 3.3 kV by 415 volt transformer. Then there will be, maybe here is another transformer. There is a breaker, there is another transformer that is also 3.3 kV by 415 volt. Now it is going to a, suppose 415 volt switch gear. From there, maybe there is another transformer that is a 415 volt by, suppose it is a 208 volt. This is another transformer. So you see, it started with 3.3 kV, it is going up to 208 volt. So there is a multiple voltage. If such a voltage is there, then how will represent the impedance? Because either we have to put the all impedance in the ohmic value. Now problem is generator, all the generator, you see this, when we manufacture and give the impedance value, they don't give it the ohm value, they give in another parameter. Similarly, when you go for the transformer, they give in another parameter, another way. We will discuss those points. So in this type of circuit, we cannot represent all this equipment impedance in ohm. Similarly, if you go only a specific, only one voltage, suppose not this, there is no different voltage, this is only one voltage like this, and then we have a cable, and it is going to some switch gear 3.3 kV. Suppose there is a cable, it is going to one switch gear. From there maybe some loads are motor is connected. Here is also some motor is connected. All are 3.3 kV. If this type of circuit all are in the same voltage, in that case we can calculate by the ohmic value. If we can find the ohmic value of this, we know the ohmic value of the cables, we can calculate from the cable catalog. Motor impedance, if we ask in ohmic value, maybe we can get from the manufacturer. So in this type of circuit, when there is a single voltage applied, single voltage is applicable, where the AC system is only single voltage AC system, in that case we can use the ohmic value which we discussed. But if it is a multiple voltage, it is not possible to calculate in ohmic value. In that case, how will represent this? For that purpose, this impedance can be represented in different ways. So which we are using for the short circuit calculation. So the impedance presentation. Now the impedance can be presented in three different ways. One is the way is called ohmic presentation, ohmic value. Okay, that is one of the ways. Second is unit is called percentage value. We can represent the impedance in terms of percentage value. We are coming to this percentage impedance or percentage Z. And third is a per unit system. Per unit system. Per unit Z. These are the three different ways we can represent a impedance. In the case of ohmic value is very simple. Suppose Z particular equipment is given, resistance suppose 10 ohm and suppose J into reactance value maybe 5 ohm. So the impedance Z is equal to 10 ohm plus 5 ohm. Suppose this is one of the equipment. Suppose this is generator. So we can simply represent this way. This is a 10 ohm. This is a 10 ohm. This is simple way. But if we go to represent the percentage impedance, what does it mean? Suppose there is a transformer. Suppose this is a transformer. It is 3.3 kV by 415 volt transformer. Suppose it is a 1 MVA transformer. Okay. This is the rating of the transformer. What does it mean? Now, if percentage impedance means when we define a specific equipment in terms of percentage impedance means the amount of voltage required to flow the full load current. This 1 MVA transformer, when you go for the 3.3 kV, it has on some full load current. Suppose F full load, that is the current. I full load is the current of this transformer on the primary side. To flow this amount of current when the secondary is shorted, that means if it is a 3 winding transformer, suppose this is a 3 winding. Suppose this is a star and this side, another side is suppose delta. Okay. So this is connected over here, this is connected over here, and the terminals has come from this is delta. So if we short it over here and if I apply the voltage over here, when we shorted this to flow the full load current, how much voltage required? That voltage is called the percentage impedance. Suppose 1 MVA transformer 3.3 kV by 415 volt. If this transformer has a 5% impedance, that means if we want to flow the full load current on the one of the winding where the other winding is shorted, then the amount of voltage required is a 5%. Suppose 415 volt is, this is a 415 volt which is shorted. I am injecting voltage from here. If this transformer has a 5% impedance means 3.3 into 0.05. These are the 15, 16. That means 165 volt. 0.165 volt is required to flow the full load current. Means 165 volt is required. If I inject 165 volt, then the full load current will flow through the transformer, through this short circuit winding. If this is the 165 volt is flowing through this, then we can see the full load current is flowing in the short circuit both the winding. What about the full load current with the secondary shorted? So that is the meaning of this. Meaning is percentage impedance means the amount of voltage required to flow the full load current when the other winding is shorted. Another way we can say percentage impedance means if we inject the full voltage when the transformer is carrying the, suppose this transformer secondary current is 1000 ampere. If we flow the 1000 ampere current, 5% voltage drop will take place in the transformer. That is another way we can say. The 5% voltage is required to flow the full load current, or 5% voltage drop will be there in the transformer when transformer will carry the full load current. This is called the percentage impedance of this. So percentage impedance means any equipment percentage impedance means directly we understand that is the amount of voltage required to flow the full load current when the other winding is shorted, or that is the amount of voltage required or amount of voltage will be dropped in the equipment when the full load current is flowed through the equipment. That is called the percentage impedance, and that is represented by Z. And per unit impedance, when that percentage impedance is divided by 100, we call it per unit impedance. So per unit impedance is nothing but the percentage Z percentage divided by 100, that is called Z per unit. And Z percentage we represent by Z percentage. And ohmic value directly we write down ohmic value equal to R plus Jx. But all these units are convertible to each other. Now how we convert each other, that we'll discuss now. How we convert one unit to other unit. Okay. Now first we consider the ohmic value is given to a circuit. So we know ohmic value Z impedance. Z equals to how much? We know Z equal to, how do we write down? Z equal to V by I. From this we get this is the ohm we get. Now this ohmic value, when we calculate ohmic value particular, this is the ohmic value formula. Now if this ohmic value, if I want to convert per unit value, how we calculate? Per unit value means we are comparing this with some basis. What is the basis? Now basis is decided based on the circuit. Now we already said when there is a particular voltage only in the circuit, we can use the ohmic method. But when the multiple voltages involved in the circuit, in that case we do not go by the ohmic value. In that case we go either percentage value or per unit value. So when we go multiple voltage levels are available, in that case when you go for the percentage or per unit value, first we have to consider at what is that, we have to consider first some basic parameters. What is the basis? What is the base? We have to consider some, because in the per unit system you understand per unit means we are comparing. We are comparing with some basic or base unit. So to compare the base unit, we consider two base parameter. One is a total system, electrical system. What is the MVA capacity? MVA capacity of the system, that is one of the basic consideration or base unit. And what is the base voltage we consider? So that is the MVA, that is we call it, we know the power energy we measure in MVA. So MVA we consider one of the base MVA. Another is a kV, we consider a base kV. These two base we have to first consider, that generally we consider this unit in such a way, these two value, so that most of the unit can cover with this. That is the basic consideration when you go for the per unit system or percentage system. So base MVA and base kV we have to consider. That means when you consider base kV and base MVA means there is a base current, I base, and base voltage, right? Base, these two things are there, base voltage and base current and base, these are the three parameters. So when we consider this ohmic value, we need to convert to the per unit system. Then what I have to do? I have to divide this ohmic value to a per unit ohmic value. What is the per unit ohmic value? Base ohmic value, base ohmic value, if I said ZB, Z ohmic value, base Z, that equal to, this equal to V base by I base. That is the simple formula for the base. This is the base impedance. So I have to calculate this ohmic value with respect to the base impedance. Whether it is a 2 times, this value is a 2 times, 3 times, 4 times, or 5 times, or half times, that we have to compare with this base unit. So base unit we decided from the base voltage and base IB or base current. So if I divide this by base voltage by base current, then it converted to per unit value, right? This is the per unit value. Now if we simplify this, how it will be coming? So this is equal to, suppose this is my original ohmic value. I can write down original ohmic value. This is my original ohmic value. And if we write this thing in the reverse, so it will be become IB by VB. Okay. Now both if you multiply by VB, this is also you multiply by VB, then what will happen? This is equal to voltage square, right? So this is equal to ohm into, now this become a, when you divide this thing, then it becomes Z per unit, right? Immediately when I divide the base unit, so it becomes Z per unit. Ohm into, this is equal to VA, right? VA, and this is equal to VB square, voltage square, right? Now if we divide this by 1000, 10 to the power 6, not 1000, 10 to the power 6, VA by divided by 10 to the power 6, it become MVA. So this also divided by 10 to the power 6. Okay, this divided by 10 to the power 6. So this VA divided by 10 to the power 6 become MVA, and this is equal to VB divided by 10 to the power 6 means I can say VB divided by 1000 the whole square. That means VB divided 1000 means kV. This is equal to kV square. This into ohm here. That means when we convert to ohmic value to per unit value, what is the formula? Z per unit. This is equal to ohmic value into MVA by kVA square. What MVA? This is the base MVA. We have to keep in mind, this is a base MVA, base kVA square. So what about the base MVA and base kV we consider? If we consider this thing with this ratio, we can convert it ohmic value to the per unit value. Once we get the per unit value, then we can calculate the percentage value. Z percentage equal to how much? Z per unit into 100. Right? Z per unit into 100 means Z percentage. That means ohm into MVA by kV square, that is a whole into 100. That is equal to percentage value, Z percentage. Now if we go in the reverse order, if we want to calculate the percentage value to ohmic value, how we calculate? We can use this formula, Z per unit. This is equal to how much? Ohmic value into MVA by kVA square. This is the base, all are base, kV base square. From here we can get ohmic value, that equal to how much? Z per unit into kV base square by MVA base. From this equation we can calculate ohmic value. Why we discuss all this point? Because when there is a multiple devices of the different voltage, I said already, suppose there is a generator, suppose there is a transformer, then there is a cable, suppose there is a motor. Suppose this is a circuit. So here normally when you go to the manufacturer always represent Z, this generator impedance given in percentage value. Suppose generator has a 12% impedance, they gave in this way. Suppose generator is a 3 megawatt generator at 3.3 kV. So they give a percentage impedance 12%. This transformer they give the impedance also in the, suppose it is 6% impedance. Now the cable impedance is given always in ohm. Suppose this is called resistance 1 ohm and the reactance is a 2 ohm is given in this way. And so, or you can say indirectly you can say total, suppose write down Z equal to suppose 10 ohm. I write down equivalent Z. The motor it has given again impedance is given, motor impedance 5%. It is given in percentage. So when we are getting this, then to calculate this thing as it is different voltage involved, so either we have to convert all this thing ohmic value or all this thing is converted to the either per unit or per impedance value. As most of them in their percentage value, better to convert only 1 unit to percentage value, then it will be easy. So if we want to convert this ohmic value to percentage value, we will use this formula. What is the Z per unit? That equal to, for this first we have to consider, once suppose this is a 3 megawatt means suppose it is a 4 MVA, right? So we can consider 4 MVA is the base and most of them are 3.3 kV. So we can consider 3.3 kV is the base voltage. So with this we can calculate the ohmic value to the Z per unit. Then this percentage value we can calculate. This is the percentage based on this base equipment. We can convert this percentage to the base MVA. This is also we can convert to the base MVA. Then all this thing we can calculate to the per unit value, then we can calculate it. So that's why this Z per unit, Z percentage or ohmic value correlation is essential. So fundamental here is we have to keep this formula in mind. Z per unit equal to ohmic value into MVA by kVA square, and Z or ohmic value equal to Z per unit into kVA square by MVA. This is one. Second thing we have to calculate, suppose this is suppose there is a transformer of 3 MVA transformer, okay. This is a transformer, 3 MVA transformer, 3.3 kV by 415 volt transformer. Now this 3 MVA it has impedance 6%. When we mention this thing means we are telling this transformer has 6% impedance based on this 3 MVA. Suppose I have considered 5 MVA base. The moment I consider 5 MVA base, then I have to transfer this impedance to 5 MVA base. How we will do that? 3 MVA base, it is a 6%. Suppose it is the same voltage, we are calculating 3.3 kV. So 3 MVA base is the 6% right now. This is the formula, Z per unit kVA square by MVA. Now in that case, Z 6% is impedance. Now when you go to the other impedance, suppose this is called Z1. Z1, this is equal to how much? 6%. This is equal to based on the 3 MVA, 3.3 kV. Now if we convert to 5 MVA, then what is the relation? This is equal to same formula. It is a MVA base by original. So it is a Z per unit. So new impedance Z2, when you go to the different base, then that equal to original Z1 into this base MVA, 5 MVA by, it is originally 3 MVA basis, 3 MVA. So you see, when the base MVA considered higher, impedance will be automatically higher. If the base MVA considered is less than the equipment MVA, then it will be less. So formula is, whatever the equipment per unit or percentage impedance given, when you convert to the base MVA, that equal to that impedance by into base MVA by old MVA. So that will be the one MVA to another MVA formula in case of voltage is same. So Z new, if we calculate, that equal to how much? That equal to Z old into base MVA or MVA, you can write down MVA base by MVA old. That is the formula for the one MVA to another MVA, consider voltage is same. But if the voltage is not same, if the voltage is also different in both the base and old, then this formula will be more complicated, because we have seen Z, how we represent Z ohmic value into MVA by kVA square, right? This is the formula we have used. Now you see, it is a impedance in inversely proportional, inversely square to the kV. That means kV it is inversely a square. That means here that equal to, if it is a different voltage, suppose new voltage and this voltage, suppose new voltage is kV new and old voltage is kV old. These two voltages are not same, different. Then that equal to, then in that case Z new is equal to Z old into MVA base by MVA old into a reverse square. That means kV square old by kVA square new. That will be additional, this factor will come. Now if the both voltages are same, this will be cancelled only this. But if the voltage in both the base and the equipment, the voltage level we are considering is different, then that will be reverse formula. That is the conversion formula for one MVA to other formula. Okay. So these are the three things. So in a brief, impedance we can represent the ohmic value, we can represent it per unit value, we can represent this percentage value. Ohmic value, if we want to calculate from the percentage value, this is the formula we have to use. For percentage and per unit, same formula. And if we calculate from the, this is the formula we have to use. And if we calculate from reverse, we can also calculate ohm equal to percentage impedance. It is a Z per unit. If we go percentage, then it equal to 100. So that per unit into kVA square by MVA. This is the formula. And mainly this per unit system or percentage system we use when there is a multiple voltage level in the overall AC overall circuit. But ohmic value is suitable when it is only one voltage level equipments. But whether you go by ohmic value or per unit value or percentage value, at the end of the day you will get the same result. The result will not be different. Okay. This is the impedance, various type of impedance and impedance meaning and the per unit system how we calculate. So this video today we will conclude over here, and from next video we will start how to calculate this short circuit current in a three-phase symmetrical short circuit current or unsymmetrical short circuit current. But another basic consideration in the case of short circuit current calculation, so whatever the voltage you use, suppose this is a generator, this is a transformer, this is a switch gear, and then suppose there is a load, there is a one load, this is another load, suppose this is a another motor, like this. When we calculate the short circuit current, we calculate the short circuit current at a particular point. It could be at this bus or it could be at this point, when we calculate the short circuit current, instant we consider at that point voltage is 0. That means this is the only voltage available which is feeding to this short circuit current at the point of short circuit. That means whether if it is three-phase short circuit means symmetrical short circuit, or it is a unsymmetrical short circuit. At this short circuit point, voltage become 0. There is no voltage. So entire voltage will be dropping in this circuit, and accordingly the current will be decided. So now we have seen all these equipment, but when we calculate the short circuit current at a particular point, we have to see from the voltage source what is the path of current. Only those path impedance will be coming into the circuit. Here these will not coming into this. Suppose there are two generator is connected by bus coupler, okay, and then there is a transformer and it is a connected over here, there is a bus coupler here, okay. Now if the bus coupler is open and the fault is over here, okay, so who will feed the current? If this bus coupler is open, only these will feed the current, these will not feed the current. So only this path impedance we have to consider. So during the short circuit, how much impedance will be coming into the circuit, that will be not decided the entire circuit. Only we have to first draw the short circuit flowing path, and on that part what are the impedance that will coming into the picture. So this is another point, and at the short circuit point we have to consider there is no voltage. So only this source voltage is present here which is supplying this short circuit current. So this is another assumptions, or this is another condition to calculate the short circuit current we need to consider. So this is the total preliminary parameters to be considered. With this we are closing this today's session, and then next in this session will be the next video, or next workshop will be for the calculation of the short circuit current. I am sorry for getting off for couple of months or nearly 1 year due to my other assignment. I hope this will helpful to all of you, and if you have any queries, please put the comments and we'll come back. And please, this session is not only for the electrical engineers, it is also suitable for the school goers, or even your sister brothers who are school levels or high school levels. They can also go through this inductance, capacitance, this impedance, this physical meaning. They can get some idea. And with that I am concluding, and thank you very much to share my channel with all of your friends and go through my channels. Thank you very much indeed. Thank you.